In this section, we look at exponential functions. Exponential functions have the form f of x equals a to the x, where x is our variable, a is the base, and a is any real number that's greater than 0. A cannot equal 1, however. And x is any real number, positive or negative. Here's some examples of exponential functions. F of x equals 2 to the x. Another function, g of x equals 3 to the x. And we can have a function like y equals 1/2 to the x. The base can be a fraction, and the base can be a decimal too. We can have a function like y equals 0.1 to the x. The defining characteristic of an exponential function is that x is the variable and it is your exponent on your function. So we had 2 to the x power, 3 to the x power, 1/2 to the x power, 0.1 to the x power. Having that exponent being our variable makes it the exponential type function. We can also have compositions of exponential functions. Here in this example, we have the exponential function 3 to the negative 2x. We're multiplying that by 100, and then we're adding 4 to it. So we have the function 4 plus 100 times 3 to the negative 2x. We also refer to this as an exponential function or perhaps an exponential type function. Graphs of exponential functions always have a characteristic shape. They level out horizontally on one side and then they just take off almost vertically. Now they might take off vertically to the left and level out to the right, as is the case in this second graph, or they might level off to the left and take off down on the right, or they might take off down on the left. At any rate, what we have is an L-shaped graph. Here we have an L-shaped graph that slopes upward. Here we have an L-shaped graph that slopes upward to the left. And here we have an L-shaped graph that slopes downward. And no matter what your simple exponential function is, that's the type of shape you're going to get. Now, if you have a composition of functions, you might get something different. Here we're going to graph a few exponential functions. The first function is y equal 2 to the x. And that's about as simple an exponential function as you can get. Exponential functions are easy to graph. If you just plot points, you're going to get that characteristic L-shaped curve. If we plug in x equals 0, we get y equal 1. And there's the point right there. If we plug in x equal 1, we get y equal 2. And if we plug in x equal 2, we get y equal 4. And if we put in x equal 3, we're off our graph here because we get y equal 8. If we plug in x equal negative 1, we get 2 to the negative 1, which is 1 over 2 to the positive 1, or 1/2. And that's that point on the left of the y-axis. And then if we plug in negative 2 for x, we get y equals 2 to the negative 2 power, which is 1 over 2 squared, or 1/4. And that would be this point right here. We draw a curve through these points, and we get our curve. And the L-shaped curve. Now, if we can apply shift rules to this graph we just got, let's say we want to graph y equals 1 plus 2 to the x. Okay, all we have to do is apply the shift rule of shifting our graph up 1. So we take all these points that we previously got and move them all up 1. Instead of the point 0, 1, we get the point 0, 2. Instead of the point 1, 2, we get the point 1, 3, which would be about right there. And we just take our graph that we had up here and shift it up 1 unit to get our new graph. We could also apply the left-right shift rules. In this example, we're going to compare the graph of y equal 2 to the x to its shifted graph y equals 2 to the x minus 3 minus 2, and that's the graph in green below. First, we have the graph of y equal 2 to the x. When x is 0, y is 1. We shift that point 3 to the right, 1, 2, 3, and down 2, and we get a point of 3, negative 1. Next, we shift the point 1, 2 from 2 to the x, and we shift that point 3 to the right, 1, 2, 3, and then down 2 to the new location of 4, 0. And then finally, we have the point of 2, 4. We take that point 2, 4, move it 3 to the right, 1, 2, 3, and then down 2, and we get the new point of 5, 2. We draw our smooth curve through, and we get our nice L-shaped curve. And you notice that the horizontal asymptote that 2 to the x leveled out to was the x-axis. Because we're shifting everything down 2, we get a new horizontal asymptote of the line y equals negative 2. The most common exponential base is not 10 or 2, but the most common base is e. And e is this kind of peculiar number, 2.718281882846. It keeps repeating with no pattern, so that makes this an irrational number, kind of like pi or the square root of 2. The exact definition of e is e equals 1 plus 1 over m, all raised to the m power, as m increases to infinity. Now we can get an approximation of e by just letting m be a really big number. We're going to let m equal 10 million. I plug m into this expression and I get 1 plus 1 over 10 million raised to the 10 million power. And if you work this out on your calculator, you get 2.71828. And it looks like e so far, but then it goes to 17. So it's very close to the exact value of e, but not exactly e. You can get as close to the exact value as you want by picking as big a number as you want. But your scientific calculator will have the exact value of e out to about 20 decimal places, so don't worry about that. We're going to look at the graph of e, y equals e to the x. And to graph this, we graph it much like we graphed y equal 2 to the x. We just pick x values and then figure out the y values. The first one's easy. When x is 0, y will be 1, because e to the 0 is 1, just like anything to the 0 is 1. So that gives us this point right here on the y-axis. Now, when we pick x equal 1, we get e to the 1 power, which is 2.7182818, but I'm just going to round it to 2.718. So that gives us the point 1, 2.718. When x is 2, we get e squared for our y value. Now to get e squared, you use a scientific calculator and you punch in either the e to the x key and then 2 equals, or on some calculators you plug in 2 first and then the e to the x key. Either way, you should get 7.389 rounded off. And for x equal 3, we use a similar process. We get e cubed for y, which is 20.086 rounded off. That's off our graph. We can get a couple negative x values in here to show up, though. We plug in x equal negative 1. We take e to the negative 1 power on our calculator, and we get 0.368, a little over a third, and that's this point just to the left of the y-axis. And we plug in x equal negative 2. E to the negative 2 power is 1 over e squared, which is 0.135. That's our y value. And that gives us this point right above the x-axis. This graph levels off to the x-axis, so that means it has a horizontal asymptote of the x-axis. It never touches the x-axis, however. And we get this L-shaped curve, just like all the other exponential function graphs we've seen. In fact, it looks an awful lot like 2 to the x. It's just a little steeper because the base is a little bigger. We'll look at an application of exponential functions, compound interest. When an amount of money, P, is invested at an annual rate of interest, R, and R is given as a decimal, for a total of 2 years, compounded n times per year, the total amount of money, A, equals that principal P times 1 plus r over n raised to the nt power. And this is best shown with an example. If we have $4,000, we put it in the bank, and that's our value P. We put it in the bank at 5% interest. Now 5% would not be 5 for r, but r would be 0.05. And we compound quarterly, which means 4 times a year, meaning n equals 4. What is the total amount in the account after 3 years? Well, since 3 is our years, then t equals 3. And since we put 4,000 in the bank, P is 4,000. So we have all our values here. We plug them into the formula, and we get the total amount A equals 4,000 times the quantity 1 plus 0.05 divided by 4, all raised to the 4 times 3 power. Now the way you calculate this on the calculator is to enter 1 plus 0.05 divided by 4 equals. Now your calculator is going to correctly follow the order of operations and divide before adding. Now it's going to take that quantity and store it, and you can then raise it to that 4 times 3 power, and we either use the x to the y key, or you might have a different key for an exponent, like a hat key. You put in the exponent key and then 12 equals. That calculates everything except the 4,000. Then multiply by 4,000 and hit equals, and you get your answer. And if you wait until you get your final answer to round, you get $4,643.02. Okay, we're going to look at where we get the value E showing up in compound interest. As you know, the compound interest formula says A equals P times 1 plus r over n to the nt power, where n is the number of compounding periods. Well, n could be twice a year, which means n equals 2. It could be monthly, which would give you n equal 12. We could compound interest daily. N would be 365. What if we compounded every minute? How about every instant? Well, if we compounded every instant, that would be known as continuously compounded interest. If that were the case, then n would go to infinity. And it seems like, well, how can we have that? The fact is, we can have that, and I'll show you how and why. First, we're going to let m equal n over r. We're just assigning a new variable. Now, if m is n over r, then 1 over m equals r over n. And if we do a little algebra and multiply both sides of m equals n over r by r, we get m times r equals n. Now I'm going to do some substitutions. Since 1 over m equals r over n, I'm going to take a 1 over n and replace that r over n with 1 over m. And since n is equal to m times r, I'm going to put an mr in its place. So now we have the equation A equals P times the quantity 1 plus 1 over m to the mr t power. Now we can rewrite that as A equals P times this quantity 1 plus 1 over m to the m power, all raised to the rt. Now where have you seen that before? 1 plus 1 over m to the m power. Well, that's E if m is going to infinity. Well, if n is going to infinity and n equals m times r, and r is a fixed rate, then m also is going to infinity. Well, the definition for E was 1 plus 1 over m to the m power as m goes to infinity. So we can take that whole quantity out right here, the 1 plus 1 over m to the m power, and replace it with E. So we get the equation A equals P times e to the rt power, where r is the annual rate. T is the years and P is the principal. You're wondering, well, how can you get continuous compounding? Well, when things are growing naturally, they don't grow at the end of each month or at the end of each day. They grow every instant. They grow continuously. So this formula, A equals P times e to the RT, actually is used more often than the periodic compounding formula. In fact, it's used so often, we call E, the exponential base, we call it the natural base. And this formula gives the growth for things occurring naturally, like plants growing, populations growing, and it also applies to things that decay naturally, like the value of your car, the value of your home. So you're going to find that this formula, A equals P times e to the RT, is going to be used an awful lot. We're going to look at an example where we use this formula, A equals P times e to the RT. We're going to look at the same example where we had the $4,000 invested at 5% interest for 3 years, except here we're going to use continuous compounding instead of compounding 4 times a year. So we use the formula A equals P times e to the RT. Our P value is 4,000. Our R value is 0.05, not 5, and T is 3. We plug those values in to our calculator, and you're going to have to figure out how to get powers of E on your particular calculator. In some you hit the E to the X key first, in others you hit the E to the X key after you put in the power, and you generally always have to use a second function key. So consult your manual or get some help on that. You plug all that into your calculator and you get an answer of $4,647.34 after rounding. And that's about $3 or $4 more than you had when you just compounded every 4 months. So you do make a little bit more money by compounding continuously.